presentations, very important ones. One about sensors in phones, and the other one was related to sensors, markup language, or actually pipeline markup language. And today, in my presentation, I'm going to focus on an applications of sensors, how we can harness sensors for an area of importance for pipeline industry, which is pipeline integrity management through geospatial sensors. So the agenda will give you a little bit of idea about what is pipeline integrity management, or sometimes called pipeline integrity monitoring. What are the activities that we use BICS for? And then the sensors, new customer needs, and some of the new trends in using sensors such as micro machine sensor for what we call non-biggable BIGs, and the role of GIS in BIM. So just a little bit of background. There is over about 400 million kilometers of oil and gas pipeline across the world. In North America, for example, we have about 600,000 kilometers. And in the Middle East, as far as I know, there is close to about 250,000 kilometers of oil and gas pipelines. The problem is that all pipelines, most, if not all pipelines, will definitely have problems, and most of the problems are related to leakage. And leakage happens for many reasons, some of which are because the infrastructure is becoming old, the welds that connect the pipelines are becoming aged. There is definitely construction defects, and also there's environmental effects. In many countries around the world, and I'm not quite sure if Saudi Arabia and Aramco also apply that, there is government mandates, operators of pipeline, that they are required to definitely do what we call leakage surveys, or to do what we call inline pipeline surveys that are required on a regular basis to make sure that the pipeline are in a good shape. For example, in Canada, some of the main lines are required to be surveyed 2 to 4 times per year to make sure that the pipeline is the integrity of pipeline is in a good condition. Of course, the overall objectives is that, to save the public and employee safety, but also some are the requirement because of legal issues such as protecting the environment and protecting the people around the pipelines. Some of the applications for these actions that are required once we know that there is a problem, first of all, most of the companies that operate pipelines have to do what we call an inspection. Once you do the inspections, you do what we call integrity assessment, and if there is any issues with the integrity, they have to go for the next step, which is repairs. And while doing the repair, they have to do risk analysis and risk prevention by doing prediction of what could happen in the future. And this is all are elements of what we call pipeline integrity monitoring, which becoming as a subset of the day-to-day activities of the pipeline, all the operation and maintenance of the pipeline. So what we're really trying to prevent? We're trying to prevent issues such as corrosion, and corrosion can definitely lead to the failure of the pipeline, such as what we see here in this image in the right bottom corner. It actually can prevent what we call buckling of the pipeline that can happen due to either loss of ground support, or could happen because of the pressure coming down on the pipeline. But also they're looking for mechanical damages. So the overall idea is we're trying to prevent that, such that we are preventing these issues of the pipeline to cause things like environmental issues, cause fires, cause leakage that can affect people around them. It can actually affect the animals and inhabitants around them. It can also affect the water around them, and so on. So by pipeline integrity monitoring, there is definitely challenges. And the challenges are that most, if not, I think 70% of most of the pipeline around the world are underground pipeline. And typically they are buried underground by 2 to 4 feet, which means that in order really to detect any leakage, right, you have to do something smart by sending tools inside the pipeline. You cannot in principle see them, so the visual inspection is not easy. So the other thing is that the majority of pipeline, I'm speaking specifically, for example, in Canada, is very hard to access them by specialized equipment, right? You only can access them, for example, by cars or by helicopters and so on, which means that the tools that can be used for this pipeline integrity monitoring have to accommodate these issues. The other thing that if you were to do remote sensing sensors used to detect pipelines leakage or pipelines problems, they are not very effective for many reasons that I'm going to mention in the next two slides. First of all, they're underground, so you really have to, detect, for example, temperature changes. You have to detect gases that are coming from oil and gas pipelines because you cannot see the pipeline itself. So one thing you have to keep in mind that definitely a small leakage can definitely lead to enormous damages, and these damages can lead to liability on these companies. So I just mentioned that remote sensing sensors can be used for leak detection. Mostly they are used for gas pipeline, and an example of that is laser systems. There is definitely some laser systems that can be tuned, right, to specific wavelengths, and this specific wavelength is reacting to specific chemical of interest. So as soon as the signal has been sent from the sensor and comes back, the changes in the signal strength can be an indication of there is a leakage in this specific area. The only problem is that these remote sensing sensors, such as laser, can definitely have to work in open air, and therefore environmental, temperature, wind can affect the precision of these systems. Most of the systems in the market right now used for leak detection, they're used for gas leak detection, and usually they have very small field of view and provide what we call beam widths in a very small range, which is 18 to about 50 inch, and you have to fly at very low altitude, which means that you have to know very precisely the location of the pipeline. There is definitely a modified version of this laser, which is called dial, which is differential absorption LiDAR, which typically use the same principle, but they use two LiDARs. And these two LiDAR has two different wavelengths. The two wavelengths, again, are tuned to specific sniffing capabilities in terms of the gas that is leakage from gas pipeline, and they definitely measure the difference in the signal strength that's coming from the two lasers. Unlike the previous one, this one is typically can be mounted into a fixed airplane, fixed wing airplanes, and therefore can fly at a higher altitude, such as 500 meters above ground level, and therefore can provide larger swaths for the scanning of the pipeline. In this type of applications, you don't have to have necessarily the precise location of the pipeline. There is also infrared cameras that are typically used in helicopters, and typically the infrared cameras record a specific spectrum of the infrared wavelengths. Within this wavelength, there is definitely certain hydrocarbons that can absorb this infrared, and those areas that absorb the hydrocarbons are an indication of that there is a leakage of either gas or oil. Also, when a pipeline leakage, typically the area of leakage, the pipeline have a change in temperature happens in this area, and typically it be cooler, specifically for gas pipeline. So if there is a leakage from gas pipeline, the area around the leakage will be much cooler than the outside, and they can also still see that there is this area are different from the areas around it. But again, the problem with most of these techniques are that they are affected by the environment around them, and more specifically wind. If the wind is very high, typically the results of this system are not very reliable. Then you have the most commonly used technique, which is what we call them BIGs, or pipeline integrity monitoring systems, using what we call pipeline inspection gauge, or BIG. Sometimes they call them also inline inspection tools. The BIG is typically a very special tool that can be used not only for monitoring everything about the pipeline from inside, but also can be used for cleaning the pipeline, which is typically required by most of the operators, that they have to clean the pipeline every 1 year or every 2 years. The overall idea of the BIG technology is that you can use them not only for detecting leakage, but for much more than that. For example, I will show you some of the sensors that typically uses these BIGs that can be used for deformation, for corrosion, for even a change in the diameter of the pipeline. Because a change in the diameter of the pipeline is an indication of future failure of the pipeline. They can also measure for buckling and dents, which typically happens when there is a failure on the ground underneath the pipeline. So the pigs are not only used for operation and maintenance, but also they use for what we call as-built. When a company builds a pipeline and you want to deliver it to the customer or to the client that paid for this pipeline, so definitely they use pigs in order to inspect it, test it, and clean before they provide it for full operation. But as part of the operation and maintenance, they are used for corrosion, for cleaning, for commissioning, and so on. So what are the sensors that typically used in these pigs? Knowing that again that most of these pigs go inside the pipeline, they use navigation sensor. This is one of the most important one, and I will tell you how and why later. But typically they need sensors to tell them where the pig inside the pipeline, right? Which means that GPS cannot work there, right? Because the pipeline, the sensor is inside the pipeline. So GPS does not work, it skips, you have direct line of sight. So they use typically inertial sensors, which are self-contained sensors, similar to what the first speech today, Mr. Blake Pollock from Samsung talked about indoor. Indoor, they rely on inertial sensors or Wi-Fi. In pipeline, you cannot buy Wi-Fi, so that's why we rely on sensors. The other type of sensor is the odometer. An odometer is simply a wheel that can move the tool inside. And then we have something called AGM, above ground markers. And these are markers that send signal to the pigs inside the pipeline to tell them that you are here at this epoch in order to control the errors of the other sensors. It has also remote sensing sensors, and I will speak about them one by one. Typically, they are magnetic flux sensors, internal diameter sensor, and something called proximity sensor. Each one of these sensors has a specific applications and have a specific output that serve the pipeline industry. And of course, the applications are numerous, as I mentioned, leakage, corrosion, and wall cleaning. How a tool looks like. So this is a typical tool, for example. Of course, the tool has different diameters, and each tool can fit within a specific diameter. For example, you have a 12-inch tool, you have 15-inch tool, you have 16-inch tool. Some of the tools can go up to even 1 meter, so they can fit inside the main feeders. But the tool is divided into a number of sensors and a number of units. The most important ones are the front ones, which control the speed, because for the other sensors to work, such as the magnetic flux unit, the speed should not exceed, let's say, 5 meters per second. Otherwise, the resolution of this magnetic field that used for corrosion management, corrosion detection, will not be effective. You have a distance recording device to tell you exactly where the tool inside, but you have also inertial measurement unit that can help specifically when the distance recording device or the distance odometer is slippage, which typically happens in oil pipeline. The wheel can slip inside and does not count the distance that traveled. And then you have many calibers, and these calibers are used for example, for corrosion, for dent, and so on. So what happens is that first thing, that when the tool descended inside the pipeline, they have first of all to know the initial location so that they can provide it for the inertial sensors. And then they push this tool inside the pipeline, descended by pressure. So they put pressure inside the pipeline, and this tool travels inside the pipeline, and typically at a speed 2 to 5 meters per second. So you can imagine if you are surveying a 1,000-kilometer pipeline, this tool can take actually 4 days, right? 4 to 7, sometimes take 7 days, which means that the power inside this tool have to work for 7 days. And then once it comes out, we have data that goes into the office, and then start the processing. So what can we see from this data? The first one, as I mentioned, is what we call magnetic flux leakage detection. And the magnetic flux, as the name indicates, is a sensor that generates very strong magnetic field. And this magnetic field is detected by what we call electromagnetic sensor. The change in the if the pipeline does not have any issues, which means that it's a concrete, and then around the concrete, sorry, it's a metal, and around the metal there is concrete. If this metal does not deteriorate or does not have any corrosion, then the magnetic field should be constant all over the pipeline. If there is any small change that happens due to loss of metal or loss of the bonding between the metal and the concrete, or even in the concrete, this will generate something called anomaly in the gravity, change in the gravity, right? Or change in the magnetic field. This change in the magnetic field can be seen as in the figure in the right-hand side as an anomaly. And this anomaly is an indication that there is a problem in this area. Another sensor that again that collect data continuously is what we call the internal diameter caliber. And as the name indicates, it's a sensor that detects if there is any changing in the diameter of the pipeline. Why is it changing the pipeline? The pipeline typically is a circle. If it changes shape, it means that's becoming either an ellipsoid, right? Or there is a small dent inside this pipeline, similar to what we have in this picture. So how do we measure it? You have a sensor continuously tucked to the bottom of the pipe or the pipeline surface, and it's connected to it. There is a spring, and this spring has a constant length. If there is any dent, such as we have in this picture, what will happen? The sensor will move down, and the spring will also change in its length. And this change in length is an indication of a change in the diameter of the pipeline. Again, you can take it and display it as an image, and this image can show me an area where the diameter has changed in the pipeline. The third one is, for example, internal corrosion. The pipeline, once it starts deteriorating, it starts change. The material starts to corrode from inside till it into a very thin, and then it broke. So how do we measure it? You use something that you use in our phones. Most of our phones, smartphones, has something called proximity sensor. A proximity sensor knows that, for example, when you have the phone and you talk, it knows that the phone actually is beside your ear. Once you start moving it away, right? Typically, the phone should switch into speaker mode, right? So how do we sensor sense the proximity? There is many ways. Some of them is laser, for example. A laser is typical sensor that can tell me how far I am, the sensor away from the pipeline. So similar to that, they use also a proximity caliber, similar to the diameter caliber. So any change in the strength of the signal coming from the sensor that shows up directly into different signal strengths that we can display it into an image, and this image can tell me exactly that there is a problem in these specific areas. So now we know, for example, if there is a problem in the corrosion, if there is a pipeline problem, right? If there is any dent in the pipeline, so how do you actually use this information? So once you know there is a problem, what does require? What's the next step? Is to fix it, because if you don't fix it, the pipeline will leak, right? And if it leaks, then it can create environmental issues. But how do you tell people to go and fix this problem? You need to tell them where, right? And in order to tell them to go where, you have to tell them to give them latitude and longitude, and tell them go and dig here, and this area contains problem, go and fix it, right? So the more precise you tell them, right, the better, right? Because it will mean that you're not going to dig very large area. And that's why we use navigation sensors, one of which is odometer. An odometer is similar to the wheel you have in your car. It tells me how many revolutions this wheel made, and therefore we can convert this into a distance, right? But the problem with this is that it can slip inside the pipeline because of the material of the oil and gas and so on can make this wheel slip. The other sensor is definitely, and most important, is the inertial measurement unit. An inertial measurement unit is a self-contained sensor used in many applications. Mobile mapping, aerial photography, for georeferencing. It's used in rockets, it's used in aircrafts. So we can also use them inside the pipeline. They don't require any external signal. They measure, this inertial sensor, they measure acceleration and angular velocity. And from the acceleration, we can integrate acceleration 2 times to give us, once to give me velocity, another time to give me distance. And by the gyroscopes, we can know the direction. So now we have 2 sensors, odometer and gyroscopes, and it's an inertial measurement unit that can give me the position inside the pipeline. The only problem is that inertial sensor by definition drift, and therefore we still need some ground control. We call them AGMs. And an AGM is above ground marker that typically can be done using GPS. So some companies do these AGMs every 4 kilometers, every 6 kilometers. And by knowing this location, we can know exactly how much drift we have. So now we have sensors that tell us there's a problem in the pipeline. We know the location. All these sensors are synchronized together, so we know exactly at what time this happens and what location. Now we can definitely send the crew to these areas. And I'm just showing you here some of the accuracy that has been achieved with some inertial sensors and some of the improved accuracies that we have been able to achieve at the University of Calgary. For example, this shows 4 sections of a major pipeline. Each section was about, let's say, 4 kilometers to 2 kilometers to 4 kilometers. And the second column here shows the travel distance, the travel time, that takes a tool. You can see that the 4 kilometers, it takes a tool to move about 21 minutes. In the bottom table, it shows you accuracy from the inertial, odometer, and AGMs, and this was a low-cost IMU. It's about 120 meter error. So imagine that you send someone with an accuracy of 120 meter, which means that they have to dig within 250 meter. It's a huge cost. And what we have been able to do through special processing, that we have been able to reduce the accuracy or improve the accuracy to 10 meter and even to 20 centimeter. Therefore, they know exactly where is the problem.
2 minutes, please.
2 minutes. I have only 3 slides.
So you are talking about accuracy. You have to be more accurate.
Yeah. Okay. So the new trend is that definitely there is major needs, and this is for municipalities, that there is major needs also and major demands right now to not only survey oil and gas pipeline, but also even distribution network, include gas, include water that goes under your houses, because there is so many incidents that happens that can actually lead to disasters in these areas. Of course, if you still use the old inertial systems and other systems, it will not work, because these pipelines are 6-inch and smaller. But we are lucky that there is definitely major development that happens in these areas, and nowadays we have sensors that not only fits inside a phone, but it can fit, you can come up with a complete navigation system that are maybe a few millimeters in size. And this can definitely be used for pipeline, small pipeline. And we have been able to do actually the first system at the University of Calgary has been commercialized right now. And this system can be used in very small pipelines, 6-inch and smaller. And this is some of the first very early tests that shows that even after 1 hour, in a small area that the pipeline is about 3 kilometers, we still can maintain about 3.6 meter error maximum, and this is humongous. This is a major improvement in the accuracy that we can achieve from phone type sensors. So I think I will stop here. I have a few other slides, but I'm going to stop here. But one quick comment. George today in the morning talked about pipeline, and that pipeline markup language. There is definitely another organization that's called Pipeline Open Data Standards, and this consortium of the major pipeline and oil and gas companies in the world that came up together and came up with standards. And these standards define how they can define, for example, what are the requirements from the inspection tool, what are the required when they do leak detection surveys, how they can store and survey pipeline materials and so on. So both are becoming very, very important, and I think it's also part of some of the ISO and OGC standards. So with that, I will stop here because I'm over time. Thank you very much.